Hello, class. Um, while I'm waiting for more people to join in, I'm going to make sure this camera is focused. Let's see. This is AP1. 10:23. Period 4. It's nice and focused. Okay. So I think I'm going to get started. Hello, class. Regarding the midterm, which was due on Wednesday, some people told me they had problems with one of the questions where the answer was 0, and it wouldn't register that you had input a 0 as having responded to the question. So I think I'm going to investigate that issue, and if it is a valid issue, I'm just going to give everyone +1 point. Okay. So kind of my intent was to maybe curve the midterm a little bit. So anyways, just beware. I'm aware of that issue if any of you had it. Actually, it's been mostly my IB class. Will you type it in the chat if you had that issue? I mean, I took the midterm, and I remember typing in 0 for that answer, and it didn't register it, and then I put in 0.0, and then I clicked out of the box, out of the text entry box, and then it accepted that. So I don't know. I just kind of played around with it until it worked. But okay. So yeah, it looks like a lot of you had it. So just don't worry about it. I will investigate, and I will give a point if necessary. Okay. So today we're going to continue learning about energy. So last time, and I think it's important to do a review. Last time we introduced energy, and we had we talked about some of the different forms of energy. So there was kinetic energy, which is the energy of motion, which is given by 1/2 mv squared. We learned about gravitational potential energy, which is given by mgy. And we learned about heat. Okay, heat as a form of energy is typically denoted by Q. So I don't think I told you that last time, but heat is usually Q. All right. And then we also learned about the total mechanical energy, which is the kinetic energy plus the potential energy. All right. And then we learned about the law of conservation of energy. So conservation is a popular term in physics. Conservation means the value doesn't change as time goes on. So we're going to learn about a number of conservation laws. In fact, you probably already have learned a few conservation laws in your chemistry class. If you took chemistry, there's the law of conservation of mass. So the mass of the reactants in a chemical reaction has to equal the mass of the products. There's a law of conservation of charge, electric charge. So conservation means that the total amount cannot change. So one way of thinking about it is the initial energy is equal to the final energy. That's sort of the mathematical statement of it. And the other way to think about it is to say that energy cannot be created or destroyed. Only transformed, okay, or transferred. I don't think I talked about transferring energy in this class, but yeah, of course, my body can lose energy. It's not that that energy was destroyed, it was just put out into the environment. You get what I'm saying? So you personally can lose energy, okay? But the amount of energy that you lost is equal to the amount of energy that something else gained, okay? So you can transfer energy from one thing to another, okay? All right. So now we're gonna, oh my gosh, we're gonna learn about a new form of potential energy. This is called elastic potential energy. Okay. So elastic potential energy is the energy of a, you could sort of think about it, it's the energy of deformation. So if you think about a rubber band, for example, a rubber band has a natural length, and if you deform the rubber band beyond its natural length, it tries to get back to where it was before. If you have a spring and you compress it, you're deforming the spring and it wants to get back to the way it was. So there's an energy that is required to deform something. So it's the energy contained in something that has been deformed. Because what happens if you take a spring that's compressed and you let it go? It goes like that. So that's you have elastic potential energy stored in something that has been deformed. Okay. All right, so I'm going to denote that by U sub E. So we have U sub G for gravitational potential energy. We have U sub E for elastic potential energy. Okay. And the formula for elastic potential energy is 1/2 kx squared. So K is, of course, if you recall, is the stiffness of the elastic band. And X is the extension. So how much has it been deformed beyond its natural shape? Okay? So this is elastic potential energy. Okay? And so that is just another item in our list of energies. Okay, so if we look at the total mechanical energy, it's going to equal all of the potential energies together. So this is actually, this potential energy represents elastic potential energy plus gravitational potential energy. Okay, so that's all the forms. One thing you really want to be careful about is differentiating between energy and force. Okay? So for example, the gravitational force is mg. The gravitational potential energy is mgy. The elastic force is kx, okay? The elastic potential energy is 1/2 kx squared. All right? So, okay? So you got to be really careful that when we're doing an energy problem, that you don't actually accidentally use the equation for force when you should have used the equation for potential energy. Okay? If you're in calculus, you might notice that these are derivatives. So there's a derivative relationship between potential energy and force, but don't worry about that. Okay, so let's do some examples. Okay. Let's suppose that we have a, maybe some of you have been to Six Flags before, and they have that ride. It's like, I want to say it's this called like Superman or something like that, where it basically just goes straight up like that. I think that's a ride. And so let's suppose that we have something that is a roller coaster cart. Okay, so here's the roller coaster cart. And there is a spring that is compressed, okay? This spring has a stiffness of, let's say 500, let's say 5,000 newtons per meter, okay? And it is compressed by 2 meters, okay? This roller coaster cart, let's say it has a single person in it, and the mass of the roller coaster cart is 100 kilograms, and it starts out at rest, okay? So, and then what happens is the spring decompresses, and it gives its elastic potential energy to the roller coaster cart. So the roller coaster cart has kinetic energy. Then as it climbs, it loses that kinetic energy, and that kinetic energy becomes gravitational potential energy. So we have a transfer from elastic potential energy to kinetic energy to gravitational potential energy. Okay? Energy is being transformed into different forms as this thing moves. Okay? So the first thing I would like to do is I would like to know how high can the coaster go? Okay? How high can the coaster go? So we want to know, because eventually it's going to stop, right? It's going to go up, 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 and it's going to reach some maximum height. Okay, and we want to figure out what is that y value. Okay, so we're going to use conservation of energy. Initial energy equals final energy. Now, the initial point is right here, and the final point is right here. Okay, so we start off at ground level, so there's no gravitational potential energy to start off with. We also start off at rest, so there's no kinetic energy. Okay, so all we have in the beginning is elastic potential energy, 1/2 kx squared. All right. Okay. Then, if we look at the stopping point, or up here, at the highest point, the roller coaster has no speed because if it did have speed, it would keep going up. So there's no kinetic energy at the final point. There's also no elastic potential energy because the spring already decompressed, so it already gave up its elastic potential energy. So therefore, all we have at the final point is gravitational potential energy. So you can see that we have converted, for this problem, we have converted gravitational potential energy, elastic potential energy into gravitational potential energy. So we have 1/2 times 5,000 times the compression, which is 2, so times 2 squared, equals m, which is 100, times g, which is 10, times y. So we can solve this for y. By the way, one of the things, when we were doing the problems last time, the mass canceled out, so it was not important to it wasn't important to know the mass of the roller coaster cart. But if we look at this problem, see how the right-hand side has mass, but the left-hand side does not have mass? So that means we can't cancel out mass from both sides. So the mass actually matters in this problem. So that's why I gave you the mass, whereas I didn't in the previous problems, okay? So crunching the numbers on that, gives y equals 10 meters. So this can go up a maximum of 10 meters. That's how high it's going to go. All right. Now, what if I said, so I know it can go at least 10 meters. It can go 10 meters up. Okay. So now, what if I said, how fast is the coaster going? When it has an elevation of 4 meters. Okay, how fast is it going when it has an elevation of 4 meters? So here's what we're going to do. We're again going to use initial energy equals final energy. Okay. So basically we're using the same initial point, but now we're considering our final point to be sort of like right here. Okay, so this is at an elevation of only 4 meters. So at that point, the roller coaster cart still has velocity. Okay, so when we get to that point, we have mgy, but then we also have some kinetic energy. Okay, we have the same initial point, so we still start with elastic potential energy. All right. So now I'm plugging in some numbers. So I have 1/2 times 5,000 times 2 squared is the elastic potential energy. mgy, so we have 100 times 10 times, and I told you the elevation this time, so it's 4, plus 1/2 times 100 times v squared. So I can solve that for the velocity. I'm not going to show all the steps, so I'm just going to do this. So it's going, the velocity when it is 4 meters up in the air is about 11 meters per second. Okay? And so that velocity would steadily decrease until it reaches 0 at 10 meters of height. All right? So that's an example of a problem that involves Man, I can't think straight today. Elastic potential energy. Let's do one more example with elastic potential energy. Okay. So let's suppose we have a skateboarder. All right. And this skateboarder has a mass of 50 kilograms. And the skateboarder is headed this way at 13 meters per second. And then the skateboarder goes up a ramp. Okay. The ramp is 3 meters tall. Okay. And then at the end of that ramp, there is, up the ramp and then onto a flat space. And then there's a spring there. And this spring has a stiffness of 750 newtons per meter is the K value for that spring. Okay. So what we're going to do is we're going to consider this to be the initial point, and the skateboarder fully compresses the spring. So the question is, how much can the skateboarder compress the spring? Okay, so the skateboarder goes up the hill, and when they go up the hill, they slow down a little bit, but then they're still moving at the top of the hill, and then they compress the spring. So what do we have here in terms of energy transfers? We start out with kinetic energy. We lose some of that kinetic energy and turn it into gravitational potential energy. And then once we hit the spring, we take the rest of that kinetic energy and convert it into elastic potential energy. You see how that works? So there's an energy transfer occurring here. Initial energy equals final energy. The skateboarder starts out at ground level. There's no compressed spring, but the skateboarder is moving. So our initial energy is kinetic energy. The skateboarder ends up elevated, so they end up with gravitational potential energy. They also end up compressing a spring, so they end up with elastic potential energy as well. And then we don't have kinetic energy in the end. The reason why is because if the skateboarder had kinetic energy, they would still be moving and therefore still be compressing that spring. So it wouldn't be the maximum compression. That's what I'm trying to get is what is the maximum compression. So this is kind of our master equation, if you will. A lot of times in physics, it's like the hardest part is just writing the master equation. Okay, you can probably do the algebra for this class, okay, pretty easily, but it's the getting the equation that you have to solve that is the toughest part, okay? So this is kind of the master equation for this particular problem. Again, not every term has mass, so we can't cancel out the mass. The mass of the skateboarder is important. 1/2 times 50 times 13 squared equals 50 times 10 times 3 plus 1/2 times 750 times x squared. All right, so I'm going to subtract this over to the other side, divide by this stuff, and take the square root. And we get that spring is going to get compressed about 2.7 meters. before bringing the skateboarder to a stop. Okay. Now, and then what might happen, of course, is the spring would decompress and launch the skateboarder back down. And when the skateboard gets back to this point, they would have a speed of 13 meters per second, but going in the opposite direction. Okay. So that's kind of interesting to think about. All right. So that's elastic potential energy. This is how bow and arrows work. This is how slingshots work. They are converting elastic potential energy into kinetic energy of a projectile. So now what we're going to do is we're going to talk about energy transfers. Okay, energy transfers between systems. As I said, the total amount of energy is conserved. But if we look at a subsystem of the entire universe, a part of the entire universe, that part can gain or lose energy. It's just that the amount that this small part of the universe gains is equal to the amount lost by the rest of the universe. Okay? So you can transfer energy between systems. And the name for this is work. So physics work is a transfer of energy between systems. Okay. So let's suppose that we have a system A, and the energy of system A is, let's say, 100 joules. Okay, that's a little bit too small. And then system B has an energy of 200 joules. All right. Now let's suppose that A gives B 70 joules of energy. So there's a transfer. Okay. Because energy is conserved, okay, if A gives up 70 joules, then now it only has 30 joules of energy, right? And B gains 70 joules, so B now has an energy of 270 joules. Okay? So that was a transfer. If we look at the total energy of the universe, the total energy before the transfer was 100 plus 200, which is 300 joules. Okay? And the total energy after the transfer would be 30 plus 270, which is 300 joules. So the total amount of energy in the universe stayed the same, but it was redistributed between objects. Okay? So we would say that this is an example of what's called work. Okay? So I'm going to write a couple of ways that you could say this. You could say that A does 70 joules of work on B. So doing 70 joules of work on B means that A gave up 70 of its joules to B. Okay. You could say that B has 70 joules of work done on it. By A. So that's an equivalent way of saying the same thing. You could say that this would be a kind of a weird way of saying it, but it does make logical sense. You could say that B does negative 70 joules of work on A. So if you do negative work on something, you're actually taking energy from it for yourself. You're a jewel thief. You jewel thief, you. Okay? So anyways, these are some different examples of the sort of the terminology that physicists use surrounding work. Okay? So work is a word that you guys use all the time, but in physics, it has a very specific meaning, and that meaning is it's a transfer of energy between systems. And then you say you do work on something, or you have work done on you. So there's, that's the lingo. Okay. So how does the conservation of energy work when we have energy transfers between systems? Well, the law of conservation of energy of the universe is always true. But if we look at an individual system, so for a subsystem of the universe, conservation of energy might not be true, okay? Because that subsystem could have energy coming in from outside, or it could be sending energy out into other parts of the universe, okay? So what we have instead of initial energy equals final energy, okay, is we have initial energy plus the work done on the system equals the final energy. Okay, so this is the work done on the system. All right. So going back to our money analogy, I was talking about the money analogy with energy. You could think about work as like a account transfer between people. Okay, so so let's say you start out with $100 in your bank account, and someone transfers $20 to you. That's like the work done. Then after that transfer, you're going to have $120 in your bank account. All right, that's the way money works. It's not like, and they're going to have $20 less in their bank account. So that's the way it works. It's a lot like money. So let's do an example. Okay. So let's suppose we have a roller coaster cart. And the roller coaster starts out at a height of 60 meters. The roller coaster cart starts at rest, and it has a mass of 300 kilograms. Okay. As the coaster descends, friction does hang on a second, I got to make sure I don't have a contradiction. Friction does negative 65,000 joules of work on the cart. Okay, so this is kind of more realistic. We were doing the problems before, assuming that when we did the roller coaster problems before, we assumed that the roller coaster's gravitational potential energy, that energy remained in the roller coaster's possession while the roller coaster descends. But in reality, what happens is that some of that initial gravitational potential energy is given to the external environment. As the roller coaster cart falls, it's pushing air out of the way, and that air is now moving. So you've given kinetic energy to the air. Energy is just sort of leaks out of the roller coaster cart and goes to the surrounding environment. Okay, so that's a more realistic way of thinking about this problem, okay? So what we want to know is, what is the speed of the roller coaster at the bottom, okay, after this work is done? So we have initial energy plus the work done equals the final energy, okay? The initial energy is all gravitational potential because the roller coaster cart starts out at rest. And we don't even have elastic potential energy because there's no springs or anything like that. So we start off with mgy. We have some work done, and we end up at the bottom having kinetic energy but no more gravitational potential energy. So now we plug in numbers. So we have 300 times 10 times 60 plus negative 65,000 equals 1/2 times 300 times v squared. One of the things I want to point out is that, again, not every term has mass. The work term does not have mass. So anytime the mass doesn't cancel out, you have to give the mass of the cart because it's actually significant, okay? So in this case, because I gave a number for the amount of work done, the mass is not going to cancel out. We solve this for the velocity. So let me do the math. And we get that the velocity at the bottom is about 28 meters per second. Okay? Type it into the chat. How do you think this velocity compares to a situation where we had a completely frictionless roller coaster? What's the effect of friction going to be on the speed of the cart at the bottom? Exactly, yeah. So friction is going to make the roller coaster cart go slower than it would otherwise. Excellent. Okay, so that's my lesson for today. So I will see you in the Zoom room in just a moment.